This video is going to give an introduction to some of the differentiation rules we can use to compute derivatives a little bit faster. So first, I'm going to start by showing you some notation. In the previous videos, I've used this notation f prime of x to stand for the derivative or slope of the tangent line. We can also use the notation dy dx, that's sometimes referred to as Leibniz notation. These two things mean the exact same thing. Dy dx is just another way of writing the derivative or slope of the tangent line. The nice thing about the dy dx notation is we're really seeing that it is a slope. It's a change in y over change in x. In addition, sometimes you might see a ddx in front of a function. That just means take the derivative of that function. So lots of different notation. This all means the exact same thing. The first derivative rule I want to give you is the power rule. If we take the derivative of x raised to a constant power, so x is our variable raised to a power, we will always get n, which was our power, n times x to the n minus 1. This is a pattern that occurs when you use that limit definition of the derivative. And just memorizing this pattern is often easier than using that limit definition every time you want to compute a derivative. So for example, what this rule is saying is if you have the function x to the third, your n is 3, so then your derivative would be 3x squared. Notice I brought the power down by 1. If you have x to the fourth, using this rule, your derivative would be 4x to the third. So the pattern is, whatever the exponent is, you bring that down, and then the exponent gets reduced by 1. So here are some more examples of problems where we can use this power rule. If I want to find the derivative of f of x equals x to the fifth, the n is 5. So using that exact same pattern, I would get 5x to the 4. 5 minus 1 was 4. Now, we can also use the power rule on radicals and on reciprocal functions. So for example, if I have the function square root of x, we can rewrite that as x to the 1/2. And now we can apply that power rule. The n is 1/2. So that n, that exponent, it can be any real number. It doesn't have to be a whole number. It could be a fraction, a decimal, a negative number. So using the rule, I bring down the 1/2, and my derivative is going to be 1/2 x to the negative 1/2. I got negative 1/2 by taking 1/2 minus 1. And we can rewrite this x to the negative 1/2 as 1 over x to the half. So when we have negative exponents, sometimes it's really convenient to bring those expressions, those terms down to the denominator and make that exponent positive. So this derivative can also be written as 1 divided by 2x to the 1/2 or 1 over 2 root x. All three of these answers on my bottom line are correct. The form of the answer is going to depend on the directions or what you're trying to do with the derivative next. All right, one more. If we have the function 1 divided by x, we can rewrite this as x to the negative 1. So the n is negative 1. And now I can use my power rule. I bring down the negative 1. I get negative 1 x to the negative 2. And that negative 2, again, it came from taking my n minus 1. So minus 1 is minus 2. And we could write this as negative 1 over x squared. And there's my derivative. All right, here are a couple other derivative rules that are going to help us solve additional problems. My first rule says if we are taking the derivative of a constant, we're always going to get 0. So if we have a constant function, it's going to have a slope of 0. Second rule says if you have a sum or a difference of functions, your derivative will be the sum or the difference of the derivatives. So anytime you have a sum or a difference, you can take the derivative of each piece separately. And then finally, my third rule says if I have a constant times a function, the derivative is going to be the constant times the derivative. So let's see how this works by doing a couple more examples. So example A, I have the function f of x equals 3 minus 2x to the fourth plus 4 divided by 3x squared. First thing I'm going to do is rewrite everything as a power of x. So all I did is took this divide by x squared and I wrote it as times x to the negative 2. So my function is 3 minus 2x to the fourth plus 4/3 x to the negative 2. So I'm going to take the derivative one term at a time. 3 is a constant, so it has a derivative of 0. The next term, we have 2 times x to the fourth. The 2 is going to stay there. This is constant times a function. So now that 2 stays there, and then I bring down the 4, and I get 4x to the third. Last term, 4/3 stays there. I bring down the negative 2, so times negative 2, and then it'll be x to the negative 3. I did minus 2 minus 1. That gave me negative 3. And then I'll simplify this. Let's see. Minus 2 times 4 is minus 8, so minus 8 to the third. And then 4/3 times minus 2 is minus 8/3 x to the third. And then we could also take this x to the negative 3, move it to the bottom. So f prime of x is negative 8x to the third minus 8 divided by 3x to the third. All right, here's another example. Now I have the function f of x is cube root of x times 2x minus 5x to the third. So in this problem, we actually have a function, something with x's, times a function. And I haven't given you any rules to work with a function times a function. I will eventually. But in general, it is much easier to work with sums and differences than products and quotients. And that is going to be true in calculus in general. Most of the time, it's going to be easier to work with a sum or a difference instead of a product or a quotient. So this problem, we have this cube root of x. That's the same thing as x to the 1/3. And that's being multiplied by 2x minus 5x to the third. So what I'm actually going to do here is I'm going to distribute the x to the 1/3, and then I'll no longer have a product. I'll just have a difference of 2 terms. So x to the 1/3 times 2x is going to be 2x to the 4/3. I did that multiplication by adding the exponents. So I did 1/3 plus 1. That gave me the 4/3. Then I did x to the 1/3 times 5x cubed. That gave me 5x to the 10/3. Again, to multiply, we have to add the exponents. So we did 1/3 plus 3. 1/3 plus 3 over 1. That became 10/3. All right, so now my function is a difference of 2 terms. And so now I can just take the derivative one piece at a time. So 2x to the 4/3, my derivative is going to be 2 times, I brought down the 4/3, so 4/3 x to the 1/3. And again, the 1/3 is 4/3 minus 1. That's 1/3. Next term, minus 5 times, I brought down the 10/3, and then x to the 7/3, and 7/3 was my 10/3 minus 1. That's 7/3. All right, so finally, 2 times 4/3 is 8/3. So I've got 8/3 x to the 1/3 minus 5 times 10/3 is 50/3. So 50/3 x to the 7/3. And there's my answer. There's the derivative of that function. All right, let's do one more. f of x equals 3 minus x squared plus 4x divided by 2x to the fifth. Again, in calculus, it is almost always easier to deal with sums and differences instead of products and quotients. And so because this is a quotient, I'm going to try to actually simplify it by doing the division before I take the derivative. And another theme in calculus is frequently, if you can do algebra to simplify before you actually do the calculus, it's going to make things a lot easier. So do your algebra before you do your calculus. So what we can do here is we can take each term and divide by the 2x to the fifth. So I have 3 divided by 2x to the fifth minus x squared divided by 2x to the fifth plus 4x divided by 2x to the fifth. So for the first term, we've got 3 halves, and then I'm just going to take that x to the fifth, move it up, becomes an x to the negative fifth. Next term, now we've got minus x squared divided by 2x to the fifth. The constant part is the minus 1/2, and then I'm going to cancel an x squared out of the top and bottom, and that leaves me with an x to the third on the bottom, or x to the negative 1/3. Or if you don't like that idea of canceling, you could subtract the exponents. 2 minus 5 gives us that minus 3. And then finally, the last term, 4 divided by 2 is 2. And then we've got an x divided by x to the fifth. I could cancel an x out. I have an x to the fourth on the bottom, or an x to the negative 4. And at this stage, all I've done is algebra. I haven't done any calculus yet. I've just actually done the division, and I've taken something that was a quotient, and I've rewritten it as sums and differences. So now we're ready to take that derivative. So first term, 3 halves, bring down the negative 5, so negative 5, x to the negative 6. Then we have a minus 1/2, bring down the negative 3, x to the negative 4, plus 2, bring down the negative 4, x to the negative 5. So let's see, 3 halves times minus 5 is minus 15 halves, x to the negative 6. Minus 1/2 times minus 3 would be plus 3 halves, x to the negative 4. And then let's see, plus 2 times minus 4 is minus 8, x to the negative 5. And there's my answer. I can also rewrite this answer with positive exponents by just taking those negative exponents, moving them to the denominator. So this answer can also be written as negative 15 over 2x to the 6, plus 3 over 2x to the 4th, minus 8, x to the 5th. Let's do a slightly different example. Write the equation of the line tangent to f of x equal 4 divided by square root of x at x equal 9. So if I want to write the equation of a line, I can use my point slope formula. Y minus y1 equals m times x minus x1. The slope of my tangent line should be my derivative at x equal 9. We've actually done problems like this in previous videos. We just found our derivative using our limit definition. And now that we know these differentiation rules or shortcuts, we can solve this problem a lot faster. So the function we're working with can be written as 4 x to the negative 1/2. Square root of x is x to the 1/2. Because it's on the bottom, I write it as x to the negative 1/2. I can use my power rule on this. I'm going to bring down the negative 1/2. 4 times negative 1/2 is negative 2. And then I did minus 1/2 minus 1. That's minus 3 halves. We can rewrite this as negative 2 divided by x to the 3 halves. So there's the derivative of my function. To find my slope at x equal 9, I'm just going to put 9 in for x. So I got negative 2 divided by 9 to the 3 halves. 9 to the 3/2, that means I have to take the square root of 9, which is 3, and then cube it. So I got 27 in the denominator, so my slope would be -2 divided by 27. So that's the slope of my tangent line. My x1, y1, my point of tangency, the x value is given to me, x = 9. My y1 at the point of tangency is going to be f of 9. So I'm going to take 9 and plug that into my original function. 4 divided by square root of 9 is 4/3. And then putting this all together in my point slope formula, here's my final answer. Y minus 4/3 equals -2/27 times x minus 9. Let's do one more example. Find all points on the graph of f of x equal x to the third minus 2x squared minus x plus 5, where there are horizontal tangent lines. Okay, tangent line, I'm thinking derivative. A horizontal tangent line would be a place where the slope is 0. Horizontal lines have slopes that are 0. So a horizontal tangent line is a place where the derivative is 0. If derivative is slope of the tangent line, then a horizontal tangent line has to have a derivative of 0. So first thing I'm going to do here is find my derivative. Derivative of x to the third is 3x squared. The derivative of minus 2x squared, I brought down the 2. I got minus 4x. Derivative of negative x is -1. Quick comments about that negative x term. You can use the power rule on that term. We have technically negative x to the 1. So you can bring down the 1. -1 x to the 0. 1 minus 1 is 0. And anything to the 0 power turns into 1. And so that's one way to get that derivative of -1. So derivative of negative x is -1. But for many people, they find it easier to look at that negative x as a linear term. And when we have linear terms, we can find the slope by just looking at the coefficient of the x. So I'm thinking that y equals mx plus b, the equation of a line. The slope is the number in front of the x. So this negative x is a linear term. It has a slope of -1. So its derivative is -1. And then finally, that plus 5, that's a constant, so that doesn't add anything to my derivative. All right, so my derivative is 3x squared minus 4x minus 1. I'm going to set that equal to 0. I don't think we can factor this, so I'm going to use my quadratic formula. X is -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that's going to give me positive 4 plus or minus, and then I get a 16. Minus 4 times 3 times minus 1 would be a plus 12, and then all over 6. So this is going to be 4 plus or minus root 28 over 6. And I think we can simplify that because 28 is 4 times 7. Square root of 4 is 2. So root 28 becomes 2 root 7. And then I do have a common factor of 2 in all of my terms. And so if I cancel that 2 out of all of my terms, I'm left with 2 plus or minus 1 root 7 over 3. So these are the x values where I have horizontal tangent lines. I would then probably use a calculator and take these x values, plug them into my original function to get y values, so I actually know where those points are. I decided to verify this graphically, and so if I draw a graph of the function f of x equal x cubed minus 2x squared minus x plus 5, I can visually see on my graph that there are 2 different places where I have horizontal tangent lines. So one right there, one right there. Those are the 2 places on the graph where I have horizontal tangent lines. And those places have x values of 2 plus root 7 over 3. That should be 1.54858, and then you can see my y value as well. And then the other place should be the 2 minus root 7 divided by, I think it was 3. That's negative 0.21525, and then you can see the y value there as well. So this is visually what we did in this previous example. By setting our derivative equal to 0, we found places where we have horizontal tangent lines. That was my last example. As always, please let me know if anything in this video is unclear.